Well, students, in the last class, we have introduced the definition of truncation error. Recall that the remainder term involved in approximating the function f of x by the Taylor's polynomial Tn of x is called the truncation error. Let us give an example. Consider the function f of x equal to root x plus 1 for x greater than minus 1. If I want to approximate this function by Taylor's polynomial of degree 2 around the point a equal to 0, then we get f of x is approximately equal to 1 plus x by 2 minus x square by 8. So this is the Taylor polynomial of degree 2 for the function f of x equal to root x plus 1. Here we have neglected the remainder term, and therefore we have truncation error involved in this representation. What is the truncation error? The truncation error is nothing but f triple dash of c by 3 factorial into x to the power of 3, right? So that can be written as f triple dash of c is 3 by 8 into c plus 1 to the power of minus 5 by 2, right? Divided by 6 into x cube. And therefore, our truncation error is written as x cube by 16 into c plus 1 to the power of 5 by 2, where c lies in a small neighborhood of 0. More precisely, c lies between x and 0, right? Next, let us see how to find the estimate for the truncation error involved in the Taylor representation. As given in the Taylor's theorem, we have to assume that the function f is n plus 1 times continuously differentiable, because the truncation error involves the n plus 1th derivative of the function f, and it will be comfortable if the n plus 1th derivative of the function f is continuous. Therefore, we have to assume that f is n plus 1 times continuously differentiable. Then, as long as we are restricting to a bounded interval, remember fn plus 1 is a continuous function. Therefore, continuous function on a bounded interval is a bounded function. So we can find a constant, say mn plus 1, such that modulus of fn plus 1 of xi is less than or equal to mn plus 1 for all xi in that interval of interest, right? Remember, this is possible because f is n plus 1 times continuously differentiable. That is why we got this boundedness property, as we have restricted ourselves to a bounded interval. So the truncation error now can be bounded by this quantity. What we did, we have just replaced mod fn plus 1 of xi by correspondingly its upper bound. Rest all are kept as it is, right? Just because we are replacing the function by its upper bound, we have less than or equal to sign here. That's all. Now, can we call this as the estimate of the truncation error? We cannot do it because it still involves x. Remember, the estimate should be a fixed number, and it should be a known number also. See, as far as the truncation error is concerned, this is replaced by a fixed number c, but unfortunately that is unknown. That is why we have to dominate it by some known quantity in order to get the estimate. Now further, we have to freeze this also, because it's still a variable. Now, as long as x is coming from the interval alpha to beta, we can again dominate this x by its maximum possible value. What is the maximum possible value that x can take? It is beta. Therefore, you can replace x by beta, and thereby you can get a fixed number. now you can see that mn plus 1 is known to us because we have assumed that fn plus 1 is a bounded function, and therefore this is assumed to be a known number, and beta is also known to us because we have restricted ourselves to a bounded interval like this, and therefore beta is also known. N is already known to us because we know what is the degree of the Taylor polynomial that we want in our approximation. A is anyway the number which is again coming from probably the interval A, alpha to beta, or something very nearby this, and that is also already fixed when we are writing the Taylor polynomial. Therefore, this is also known to us. So everything is known and they all are fixed, and therefore this is a valid estimate for us for the truncation error. Let us go back to our previous example and try to find an estimate for the truncation error. Recall that in our previous example, we have taken f of x equal to root x plus 1, and this function is defined in the interval minus 1 to infinity, right? So therefore, we will consider the function f to be defined on the interval minus 1 to infinity. Recall that we were interested in approximating this function f of x by Taylor polynomial of degree 2, and thereby we got the truncation error as x cubed by 16 into 1 plus c to the power of 5, okay, where c was a fixed number there. Just we will consider this expression as a function of two variables. One is x, which is going to vary from minus 1 to infinity. And for the analysis purpose, we will also consider this entire expression as a function of xi also. But in our Taylor theorem, it is fixed, but unfortunately it is unknown. Okay, so here we will assume that it is a variable, and thereby we will try to find a bound for that. Okay, remember we have to find a bound for this derivative by considering this function as a function of xi, right? So that is why I have just taken it as xi here, and it is going to vary where, let us put xi also in say minus 1 to infinity, and see can we find a bound for this function. Okay, well, as far as the theorem is concerned, it should come from a small neighborhood of 0. Why? Because we were interested in that example to approximate the function f around a is equal to 0. That is why we got this truncation error. Otherwise, you would have had x minus 8, the whole cube you would have had here. Okay, going back to our question, can we find a bound for this function if x and xi belongs to minus 1 comma infinity? That is the question. See, the neighborhood of 0 may extend up to minus 1 also. Okay, so you have to basically find the upper bound for the third derivative of f as per the first step. So what is the third derivative of this function? It is given like this, and unfortunately it is not bounded if you include minus 1 also in your neighborhood of 0, right? So in particular we are working in this interval, therefore we may go very close to minus 1. Therefore there is a danger that this function is not bounded in the interval in which we are interested in. So therefore we cannot find an estimate for the remainder term in this particular case. However, if you just restrict yourself to an interval which is slightly away from minus 1, right? So we are interested in this interval minus 1 to infinity. Suppose you just restrict yourself to an interval, say minus delta to infinity, then you can find a bound at least with respect to xi, right? that bound will be basically replacing xi by delta, because f triple dash of xi is, if you recall, it is 1 by 16 into root 1 minus xi to the power of 5, right? And this is a decreasing function, and it blows up, sorry, there's a plus here, and it blows up at xi equal to -1, but we are restricting it to some minus delta, where delta is given to us like this. Therefore, it attains its maximum value actually at minus delta. So that is how we are getting this. Okay. Can this be an estimate? No, because, well, we got rid of the variable xi by dominating it by delta. However, we still have x. Okay. So in order to find an upper bound for this quantity by replacing x by the maximum possible value that x can take in the interval of interest, again we will face problem, because we are extending our interval up to infinity on the right hand side. Therefore, what is the maximum value that x can take? Well, it can tend to infinity. So again, at this stage, even after restricting ourselves away from -1, we still cannot have an estimate for the truncation error. In order to get an estimate, we further have to restrict ourselves to a bounded interval. That is, we started with -1, we restricted ourselves to some minus delta, whereas we had still interest up to infinity, and that is again giving us problem in freezing this part. Therefore, we have to restrict ourselves to some bounded interval, say minus delta to b, for some b greater than 0. I mean, greater than minus delta is enough, but I just put 0 because we need 0 to sit in this interval, because Taylor expansion was around the point 0, right? So once we do this restriction, then x can take value at most b in this interval. Suppose you are interested in approximating your function in this interval, then you can dominate your truncation error by this quantity. Now you can see that as long as you are restricting with this interval where delta and b are known to you, this is a fixed number, right? Therefore, this is an estimate for your truncation error while approximating the function f of x equal to root x plus 1 around the point a equal to 0 by Taylor polynomial of degree 2 in this interval. Then your truncation error can be at most this value. We don't know still exactly what it will be, but we can say that it can at most have this value. That is what we get from this analysis, and this is finally called the estimate for the truncation error. The next concept is the Taylor series. Let me just define it. Let f be a C infinity function in a neighborhood of A. What is mean by this? F is a C infinity function means f is differentiable as many times as we want, and the derivatives are also continuous functions. Now the question is, if this series converges, then what is the limit of this series? Well, from the basic theory, we can see that if this series converges, then its limit will be f of x, because it is written at the point x here. Therefore, it is f of x. So this is something which we know from our basic course on real analysis. Let's take an example. Consider the function f of x equal to cos x. You can see that the Taylor series expansion of cos x around the point x equal to a is given by this. You have cos x equal to cos a minus f dash of a, this is sin a, into x minus a, plus f double dash of a by 2 factorial into x minus a square, that is cos a by 2, and so on. Let's take in particular a is equal to 0, and you see that the series representation of cos x is given by this series. So this is the series representation of cos x. We all know it. In particular, let us take a equal to 0 and we will try to write the approximation of cos x as the fourth degree Taylor polynomial, and it is given like this. Remember, we have to take k equal to 2 in this case, and what we have neglected in this approximation is the higher order terms, that is x to the power of 6 by 6 factorial plus x to the power of 8 by 8 factorial, and so on. This is what we have neglected as far as the series is concerned, and that from the Taylor's theorem we can see that we can also write this neglected term in the form of the remainder or the truncation error. So it is from the Taylor theorem statement, it is the fifth derivative of the cos function c by 5 factorial into x to the power of 5. That's the remainder term or the truncation error. That is going to be minus sine c divided by 5 factorial into x to the power of 5. However, we prefer to take the remainder term in this form. It means what? We have taken the remainder term as f6 at some point c divided by 6 factorial into x to the power of 6. Recall from the statement of the Taylor's theorem, we are supposed to have f5 c by 5 factorial into x to the power of 5, and that will happen to be minus sine c by 5 factorial into x to the power of 5. In fact, in many calculus books and also real analysis books, they write this as the remainder. However, from the numerical analysis point of view, we prefer to take this as the remainder. Now, immediately there are two questions coming in our mind. One is it correct to take this as the remainder because the Taylor theorem says this as the remainder, right? And second thing is, why are we preferring this form and not this form? Well, the second question I will answer in the next section when we are talking about the order of convergence and the big O and small o. Whereas the first question, that is it correct to take the remainder term like this instead of this? The answer is yes. You can always take this as the remainder in this particular example. Why? Because the next immediate term, which is supposed to have sign, is vanishing because we are approximating the function around the point a equal to 0. Therefore, the immediate next term, which is supposed to be x to the power of 5 by 5 factorial into f5 of a, and that is sine of a, sine of 0 is 0. Therefore, the next term in this series is going to be 0, and the next even term survives here, right? So therefore, the leading term in the series, which we have neglected, is having x to the power of 6, not x to the power of 5. That allows us to take the remainder term as either this or this. Both are correct. This can be seen by going through carefully the proof of the Taylor's theorem. Let us hold our discussion here and go back to the Taylor's theorem and see how the remainder term can be written in this form in this particular example. Let me open our notes and go through the proof first. Recall the Taylor's theorem says that if f is n plus 1 continuously differentiable function on an open interval containing a and x, then you can always find xi. Well, in our discussion, I have denoted it by c. Keep this in mind. So the theorem says that there exists a xi between a and x such that f can be written as the Taylor polynomial of degree n plus the remainder term or the truncation error. Okay, so how will you prove this theorem? Well, there are many ways to prove it. Let us take this proof. Well, let us prove the theorem for x greater than a. Once we do this in a similar way, we can also construct the proof for the case when x is less than a. What we do is first you define a function g like this: f of t minus tn of t minus a into t minus a to the power of n plus 1. Now, what is a? A is a parameter which we will choose in such a way that g of x is equal to 0. So what you do, you put t equal to x in this expression, you will get this minus tn of x, sorry, this is x, minus a into x minus a to the power of n plus 1, right? Now you make this as 0, and from there you get the expression for a like this. So once you have a, you can see that by plugging in this expression for a, we always have g of x is equal to 0 for a fixed x. You give me a x, I will give you a, like that it goes. And you can easily see that g of a is also equal to 0. That you can directly see from the expression. You just put t equal to a here. This term right away goes to 0. In this term, every higher order term has x minus a. So everybody goes, only the constant term survives, and that is f of a. And here you have put t equal to a. Therefore, this also is f of a minus f of a. So this will also go to 0. So therefore, you have 2 points at which this magic function g, which we have defined, vanishes, right? So the function g, you can see that it is a continuous function. It vanishes at a, and also it vanishes at x. And remember, it is a continuous function. Therefore, by Rolle's theorem, we can find at least one point, say C1, such that g dash of C1 is 0, right? That Rolle's theorem will give you this guarantee. Now what you do is you consider A to C1. Okay, this interval. Here again, g dash of A is 0. Again, you can see directly from here, the expression, you differentiate g with respect to t and put t equal to a, you will see that g dash of a is 0, and we already have g dash of C1 is 0, thanks to Rolle's theorem. So g dash, again, it's a continuous function by our assumption that f is n plus 1 times continuously differentiable. That is where we are using that hypothesis to make sure that all the derivatives of g up to order n plus 1 exists, right? So g dash also vanishes at a as well as at C1. Therefore, its graph is something like this. Again, you can see that by Rolle's theorem, you get a C2 at which g double dash of C2 is 0. So that's what we are saying here. Continuing this way, you can see that there exists a Cn plus 1 such that Gn plus 1 of Cn plus 1 is 0, right? Why we go only up to n plus 1? Because we know that f is continuously differentiable up to n plus 1. Therefore, you can go at least up to this. Beyond this, we don't know. And we see that there exists at least one point Cn plus 1 such that Gn plus 1 of Cn plus 1 is 0. Again, Rolle's theorem. But what is Gn plus 1 of t? Okay, you can go back to the definition of G. You can differentiate G n plus 1 times and put t is equal to Cn plus 1, and you get this term, right? But you know that this is 0. From there, you can get A equal to this. You already know what is A. Remember, when we are forcing G to vanish at X, that gave us an expression for A, and that is f of x minus Tn of x divided by x minus a to the power of n plus 1, right? Equate these two, you will get the desired Taylor formula. Okay, so now what we have to do, why we came here to prove Taylor's theorem now, is because we want to see that when we put f of x equal to cos x, then we can write the remainder term for the fourth degree Taylor polynomial as f6 of c divided by 6 factorial into x to the power of 6 instead of f5 of c divided by 5 factorial into x to the power of 5. Okay, so this is where we decided to come to understand the proof of Taylor polynomial. Now, in order to prove this, what you have to do, you just have to manipulate the definition of G. That's all. See how you will write G of t equal to cos t minus, this is T4 of t minus, then you are supposed to write A into t minus, we have 0 in our example. Instead of 5, you put 6 here. Okay, so that is what the key idea here, to get this remainder term. You will see that the entire proof goes through without any problem, thanks that the next term is, that is the fifth derivative term, is actually vanished. Because of that, your proof exactly goes through even for this definition of G. If that was not vanishing, that is f5 of A, if that doesn't vanish, then you may have to stick with only this formula. Just because f5 of A is vanishing in this particular example, you can also define G like this, and that exactly the same proof will go through. This is where we are gaining one higher order in the remainder here. Okay, I hope you understand. If you don't understand, you can ask me in the live session. Coming back to our example, so it doesn't matter in this particular example whether you take the remainder term as this or the remainder term as this. In general, if I ask you any function and ask you to find the remainder term, what best you can do is you write the polynomial and see in that process what is the next term that is sitting first in the truncated series. Based on that term, you write the remainder term, and that is going to be preferred in the numerical analysis course. If you write this term, although it is correct from the calculus point of view, in numerical analysis course, we don't prefer this. The reason I will tell you in the next section. In general, when we are expanding the cos function in Taylor polynomial, then you have the Taylor polynomial plus the remainder term is given like this. Okay. Similarly, care should be taken in writing any function where certain terms vanishes in between. However, if we take a not equal to 0, where sign is not vanishing, then the fourth degree Taylor polynomial for cos x is given like this. Since sign is not vanishing at a, we have to have our remainder term like this only. Okay, in the last case, we had the higher order term as remainder because sign was vanishing at a. If that doesn't happen, then you have to take the immediate next term as the remainder term. So this you have to keep in mind. Therefore, Taylor's theorem tells us that given x, there exists a c between x and a such that cos x is t4 minus, this is the remainder when a is not equal to 0, is such that sine A is not equal to 0. If sine A is 0, then we will be taking the sixth order term as the reminder. Okay, so this should be followed in any example carefully. We also need bivariate Taylor formula when we are doing Rangikuta method in the last chapter. Because it will come at the end of the course, so you may forget it if I introduce it here. However, one variable Taylor's theorem is used everywhere in the course. That is why I have spent some time on this. And you also have to be careful in handling Taylor's theorem from the numerical analysis point of view. This is also the reason why I have spent some time and explained the Taylor's theorem, although I know that you all know this theorem very well from your previous course.